Hello, can you see me now? Can you see my desktop? Is everybody out there? Okay, let's see. Okay, so today we're going to pick up where we left off on Monday. Okay, so we're going to keep talking about virtual memory. Oh, actually, first let me start off by saying, does anybody have any question about the homework assignment? Is there any question that's come up that could possibly answer about the programming assignment? Okay. If you have, as usual, if you have questions about the program assignment, feel free to send me an email. If you want to actually talk about it, you can always arrange to meet with using Zoom. Okay, so today we talked about this intro chapter. The we talked about this intro chapter on Monday, and today we're going to go to this chapter here, which actually explains how you do the virtual memory system. How can you create an address space? How can you create a sense of virtual memory? So let's go back to this chapter and review what we want to do. Okay, the idea is really this picture and this picture. Okay, this is physical memory. And in this physical memory, there's the operating system and 1, 2, 3 processes. And then there's some empty spots in physical memory where there could be more processes. Each process runs in its little chunk of physical memory. Inside that physical memory, inside that process, the process looks like this. This is it. Now, the key is the process thinks it actually sits at address 0. The process actually thinks it sits at address 0, even though the process sits, for example, here at the address 128,000. That's the address the process C sits at. It thinks it's sitting at address 0. It thinks it's sitting up here. What that means is
It doesn't know.
when the compiler compiled the code that sits in here, the compiler assumed that all the variables were sitting at addresses, in this case, between 0 and 1,000. So the compiler compiled the program so the addresses built into the binary of the file have addresses between 0 and 1,000. Okay, so that's what the program thinks. It thinks that all the variables that sit inside here are between here and here. Similarly, it thinks that the stack is up here and growing down this way. So it thinks the bottom of the stack is at address 16,000. And as the stack grows, the addresses shrink. So that's what this program thinks. But the program is really sitting in here, okay, with the code up here near the top, okay? So this is called the address space. The program thinks its addresses are between 0 and 16,000, okay? We need to create that illusion. Now, how can this code, which thinks it's based at 0, run here when it's based at 1,208? If it accessed the variables all seem to be down here because all the variable addresses are between 0 and well, remember in this picture, they goofed up a little bit. In this picture, they made the virtual address space look like it's 16,000 kilobytes. But in this picture, he's making them 64,000 kilobytes. In the next chapter, he kind of fixed that. But in this chapter, this one should have been 64,000 bytes. That would have made more sense. Make this one 64,000 bytes. Okay, so these addresses, the program, when it accesses a variable like x, and it thinks that x is at a memory location like, say, 400, if the code was in here and it accessed variable x, 400's up here. Okay. So there's essentially going to be two ways to solve this problem. The really old-fashioned way was when this program was copied into memory when it was first started, and it was copied into memory, all the addresses up here would have to be translated as they were being copied. Remember, that was called relocating loaders. Okay, when you copied the program from the hard drive, remember the program itself starts on the hard drive. When the program was copied from the hard drive into physical memory, while it's being copied, all the addresses were well, you'd have to add 120. See, what you do is you'd add 128,000 to every address in here. So every address in here would have 128,000 added to it, and it would then be an address in here. every address in here, if it was loaded into where B is, would have 192,000 added to it. Okay? That would relocate the addresses so they're sitting inside here. Okay, but relocating is bad. Doing this relocation is really bad. For example, we mentioned in class the other day, if you want to load a big program, they would need this space, and this space. And this space is in the middle of it. You could push this one up and have 3 spaces in a row that are empty. So you could load a really huge program. But to move this program from here to here, you'd have to copy it. But as you're copying it, you'd have to do the address translation all over again. So that's tremendously slow and inefficient. The copying alone is bad enough, but not only would you have to copy it from this area to this area, but as you copied it, you'd have to do the address translation on the fly. Okay, so there's a better way to do the address translation than to have a relocating loader, and that's to have the hardware do the address translation. That's this next chapter, to have the address translation done by the hardware. Now, what that means is this program, when it's on the hard drive, it's put there by the compiler. It thinks all its variables are between 0 and 1,000. So all the program thinks it's living in this virtual address space. Okay, you copy the program into here just exactly the way it is. So even though the program is based at 128,000, all the addresses in the program are going to be between 0 and 64. Okay, and same with B. B will be sitting here between 192,000 and 256,000, but all its memory addresses in the code think they're between 0 and 64,000. Okay, but the address translations are going to be done on the fly as the program runs. Okay, so let's switch to a different picture. That's this picture here. The address translation is going to be done by this step here. Okay, the program, you see, I can get both these pictures. The program is sitting in memory here. So in our case, that would be the program is sitting in memory. I lost my mouse. Okay, the program would be in memory somewhere over here. So this is physical memory over here. So these processes are sitting over here in different parts of physical memory. Okay. Oh, actually, I want to switch to paint because I want to be able to draw on that picture. So let me load that picture using paint. Okay, so what over here, this physical memory here is this, oh, losing the, that's the only problem with paint. See the mouse, you can see my mouse pointer. And then when I switch over to paint, it's a ghost of a mouse pointer. There's just barely a ghost of a mouse pointer. See, it's over here in physical memory. Okay. Yeah. So here would be one program in physical memory. Over here would be another program in physical memory. And maybe over here would be another program in physical memory. Okay. So that would be this idea here that there's 1, 2, 3 programs in physical memory. So one program would be in one range, another range, another range. Okay. All right. Now, this program here, which is over here, it thinks all its addresses are referring to addresses down here. Okay. What that means is that when the CPU issues address like the program counter, the CPU is actually issuing addresses from 0 to 60, in this case, from 0 to 64,000. The CPU, this is the weird thing. You have to imagine that the CPU thinks it's in this address space. So every address loaded in the CPU, now the CPU got its addresses from the code that's in memory, but the code in memory was put there by the compiler, and the compiler assumed this picture here. So the CPU wants to access that memory location over here. It's going to issue an address like, say, 700. 700 would be an address over here. Okay, but that 700 really is 700 units down from, 700 bytes down from the top of this physical address. So an address here, a virtual address here of 700 would be a physical address here of 128,700. That would be the address down here, 128,700. Okay, but in here we'd have be the address 700. This guy is going to do the translation, and what we're going to do is we're going to put two registers in here. So I'm going to draw a little box here. So I'm going to draw a little box to represent two registers. So in the memory management is two registers, and the registers have names. See if I can add a name to them. This second register is going to be called the bound register. And this register, the first one, is going to be called the base register. Okay, so what we're studying is something called base and bound. Okay, so the memory management unit has two registers in it, base and bound. The base register is this base address. Okay, so in our case, over here, like this base register might have in it 1,200. Okay, that would be what the base register is. So the base register, that would be this process here. His base is 128,000. The bound register is over here in this picture. What's the bound, the upper bound on memory you can access? You can access memory from 0 up to your upper bound. Okay, I'm going to use what's in this picture. I'm going to use an upper bound of 64,000. So in this picture down here, the bound register would have 64,000 in it. Or if actually it's 64 kilobyte, which is not quite the same thing as 64,000. Okay. So the base register is, and this should have been 128 kilobyte, which is really slightly different than 128,000. Okay, so you have the base and bound register. When the CPU issues an address like 700, so the CPU has an address like 700, that's in the program counter. 700 goes through here on the virtual address bus. Then 700 goes into here, and it is going to be translated. See, 700 would be an address up here. 700 would be an address way up here. But 700 is supposed to be this address inside process C. What we're going to do is the memory management unit is going to take that virtual address, add the base to it, check that it's not going past what its bound is, and then issue the physical address. Okay. Now down here, I'll write, there's a formula. There's a nice little formula we can think of for this. Okay. Okay. We're going to issue a physical address. We want to compute a physical address. The physical address is computed from the virtual address. And here's what the calculation looks like. I'm going to write it in C code. I'm going to take the virtual address and ask, is it less than the bound? So I'm going to use the C's ternary if operator. So I ask, is the virtual address less than the bound? If the virtual address is less than the bound, then the physical address will be equal to the base plus the virtual address. You would add 700 to 1,000, 120,000 to get the physical address. On the other hand, if somebody did something dumb, so their program is in here, but they're trying to access a memory location that's more than 64,000 bytes away from their base. So they're essentially trying to access memory past their limit here. Okay, so if the virtual address is greater than the bound, there's a problem. That's this signal here. You raise interrupt or throw, if you want to write it in Java-ish, you'd say throw an exception. You raise this interrupt or throw an exception. Okay, and I'll put that in. Okay, so here's the calculation that gets made. There's the calculation that gets made by the hardware. The hardware does this calculation. A virtual address, which thinks it's living in this address space here, the virtual address space. The CPU has nothing but virtual addresses in it. It sends its virtual address out on the virtual address bus, and it goes into the memory management unit. The memory management does this calculation. It checks if the virtual address is less than the bound. That needs to be true. Okay, if it's not true, you interrupt the process, and essentially this interrupt causes the program to crash. You've got a memory violation. Now remember, this is all being done in user mode. So now we can see how the CPU in user mode gets told when there's something violating what user mode. Remember, user mode is, we said that in user mode you can only access certain memory locations. We never said how that works. When you're in user mode, you can only access certain memory locations. Now we know how it works. When you're in user mode over here, you can only access memory addresses between your base register and your base plus bound. Okay, so you're stuck within this little range of memory addresses from your base register up to your base plus the bound register. Okay, so this is the thing that, now when this interrupt is raised, like any other interrupt, that switches the CPU from user mode to kernel mode and directs you into the operating system code. That directs you into the operating system, where the operating system then terminates your program because you did something really wrong. Your program issued an invalid memory access. It tried to jump out of its memory range. So the CPU just shuts your program down. Okay, that bus there, that 1-bit interrupt is the thing that in programming you would call this throw an exception. You would think of this as throwing an exception, but in hardware land that's referred to as raise the interrupt, because usually you think of this thing as 0. This is a binary bit. When it's 0, everything's okay. You raise it to 1. You raise the interrupt to 1, and that's the signal that the CPU should halt the program. Okay. Okay. If we want, we can say the oh, now remember, if you switch to another process, then you have to switch these base and bound register. Now, over here, every process has the same size of memory, 64. Every process has the same size of memory. And in some cases, you don't even need a bound register, because if you assume that every process has the exact same size virtual memory space, then you don't need a bound register. The bound value is fixed for all processes. But when this stuff was done in the old days, it was assumed that the different processes would be different size. Some processes would be small and some processes would be large. So you didn't have to have every process exactly the same size. So you had a base register for where the process began, and then you could have a bound register that said how big a process was. So you could have a process that was 2 of these chunks here. By having a bound that was 128K, a process could start here and go up to here. It could occupy 2 of these regions here. Okay, so depending on the architecture, you could have just a base register, or more often you had both a base and a bound. These 2 registers are part of the state of this process. So when you're running process C has all its register values in the CPU, but process C has these two other registers, which are in the memory management unit, that are part of process C. When it's time to do a context switch from process C to process B, you'll have to go to the process control block. Okay, yeah, you over here. We can remember we can imagine that we have a we can have a bunch of process control blocks. Oops, what am I doing? Oh, I'm still. We can imagine that there's a bunch of process control blocks, one for each process. Okay, so these are the process control blocks, and when you're going to switch from like this would be, this one is process. Oh, let's see. This one's oh, I'm still in the wrong tool. Okay, this is process A. No, wrong tool. Why am I stuck in that tool? Where's the free? I forget. Where's the free drawing? Isn't it this one? There. Oh, I'm sorry. Okay, there. Okay, there's the control block for process A. There's the control block for process B, and there's the process control block for process C. Okay, so when you switch from process C, for example, right now we're process C, we're running process C, we have process C's stuff in the memory management unit. When we switch from process C to process B, everything in the CPU gets copied into this process control block, and the memory management unit gets copied into the process control block. So the process control block is really two little states. The process control block has the CPU state in it and the memory management unit state in it. I'll draw it like this. Okay, so a chunk of the process control block is the CPU state, and a chunk of the process control block are the memory management unit state. Same with these other ones. The process control block is in two pieces. Okay, the CPU part and the memory management unit part. So when you switch from process C to process B, process C's registers are copied into here. Process C's memory management unit is copied into here. Then process B's memory management unit is copied into here, which will have 192,000 inside here. I don't know if I can change what's in there, but that would change what's in the memory management unit. Can I actually edit what's inside those? It's putting another text box on top of the old text box. Does anybody know, can you edit a text box that's already been put in there?
I don't think you
Like
can.
right now, it's just writing on top of that text box, I think. Yeah, it's just writing on top of it, which is not what I want. Okay. So if you switch from process B to process C, you're going to replace that number with the number 192,000. Okay, so then you'll put a different number in there. So you'll switch it to 190. Okay, so you'll update the base register. So when you switch from C to B, you copy B's memory management unit into you copy B's base and bounds registers into the memory management unit. So B's base is 192 kilobytes. okay? And then you copy B's registers into the CPU, and then you finish doing a context switch. Now this same 700 address, now that 700 address is 700 units away from 192,000, not 700 from 128,000. So notice that this virtual address has now been mapped to two different physical addresses by switching from one context to another context, by changing the contents of the memory management unit. Okay, by changing the base and the bound register. Okay, okay, this is actually a really simple idea, and it turns out that computers don't use this anymore. They used this back in the 60s. It was very simple, very elegant. It's super fast. Doing this little bit of arithmetic inside the memory management unit every time you access a memory address seems like it might slow you down, because this calculation here is done every time the CPU has to load a memory address. Every time. So this calculation is being done, millions of times a second. But it isn't slowing things down. It's done in hardware in a very efficient way. I mean, it's not done anymore because nowadays people don't use base and bounds. What we now use is something far more complicated than this. So the calculations are even more complicated than this. On you do a page table lookup on every address translation, but it turns out it's still very fast. So this calculation down here was done in hardware, and you would check that inequality in hardware, then you would branch to either returning this address or raise the interrupt, but that would happen in just tiny, it didn't slow the CPU down in an appreciable amount, okay? So since it's done directly in hardware, it can be done super efficiently, okay? And then you have what you really want. Your processes all think they're in virtual memory space. The compiler can write code as if every process ran between 0 and whatever your upper limit was here. Every process was thought of as being based at 0. That made compilers easy to write. Okay. Then programs, when they ran in memory, are the really important thing to realize is that when programs ran in memory, they were restricted to their region of memory. One program running in here was really limited to that chunk of memory. When a program is loaded into physical memory, because of the memory management unit, that program cannot see any other program's memory. Okay? So this does address translation. This gives us our mechanism, this gives us our abstraction of address translation. These two registers, the base and the bound register, they solve the problem. They create the idea that every process sitting in physical memory really thinks, well, it thinks it owns all of what this is what it thinks virtual memory is. It thinks virtual memory is from here to here, and as far as it knows, it owns all of virtual memory. Okay, so every process running in the CPU just assumes that from its point of view, what it sees when it looks over here is this. Another way to think of it is that if I switch these two pictures and kind of move them side by side this way, when the CPU looks over at memory, this is what it sees. The CPU, whoops, the CPU is issuing virtual addresses. It thinks it's talking to that virtual address space. Okay, that's what the CPU thinks. Okay, but in reality, the CPU is talking to the memory management unit, and on what's on the other side of the memory management unit is that physical address space. So when the CPU thinks it's talking to a virtual address space, the memory management unit actually maps that virtual address space into one of these chunks of physical memory. Okay, and that's a good way to think about it. Kind of like think of it this way: when you cover up the memory management unit, the CPU thinks it's talking to this. We call that the virtual address space. Okay, the CPU thinks it's talking to that virtual address space, but in fact, the CPU is talking to the memory management unit, and the memory management unit is talking to this address space, the physical address space. Okay, and the virtual address space is moving around in here, depending on which memory management, depending on how the memory management is set. If it's set for, right now it's set for process B. So now all the addresses that come out of the memory management unit go into here, into B's region. Okay, and then if you do a context switch back to C, then you'll update the memory management unit, and then all these, then this virtual address space, gets mapped back to a different physical address space. You jump from here back to that one. Okay, so this is actually it's a very simple, clever way to create protected memory, to protect one process from another. It actually accomplishes two goals. It makes life easy for the compiler. Okay, the compiler assumes that it's writing code for a virtual address space. Okay, so it makes life easy for the compiler. The compiler was doing that anyway, even if you were using a relocating loader, because that's how you can write a compiler. You write the compiler to assume a virtual address space. But now we get the compiler working with the virtual address space, but then the processes are in physical memory protected from each other in an efficient way. This is very fast, and now we have the processes in physical memory, and they can't touch each other. Okay. Now, if this is really good, why don't we still use it? Okay. And it's got it's got a couple failings. It's got one real major failing. It's got a minor failing that we'll fix in the next chapter, which turns out to be, there's one minor failing that's a little bit easy to fix, but it's got one major failing. Okay. Here's what the major failing is. Suppose a process comes in that wants essentially the size of that wants a virtual address space that's bigger than one of these little blocks here. Suppose it wants a virtual address space that's the size of 3 of these blocks. Well, like we said with the relocating loader, if you want to load a process that needs all 3 of these, that needs 3 blocks, but there's somebody in the middle of them, you can move him from here to here. Okay, you can move him from here to here, and then you have 3 blocks free. You'd have process A starting at 256K, and then starting at this one, you'd have room for a big process. Okay, now, first of all, how would we relocate A? Now, when we had a relocating loader, which we said was bad, we would move process A by copying him up to here, but as we were copying him, we had to translate every address that was in A. Okay, that's really bad. With the base and bounds process, we can still move A, but move him in a much better way. We have to copy him from here to here, but then all we have to do is change the base register once. So we copy him without any translation, okay, and then we update his base register from what it was, 320,000. We update his base register to 256,000, and now he's running in this block here, and these 3 are free. Okay. That's called defragmentating memory. Right now, we have what's called fragmentation of memory. There's 1, 2, 3, 4 free chunks of memory, but the free chunks of memory are broken in pieces. The breaking of free memory into pieces is called fragmentation. Okay, this has a problem with fragmentation. As processes get loaded and unloaded, they end up fragmentating memory. Like here, first of all, when the computer first started, it probably put the first process here, then put the second process here, then the third process here, the fourth process here. But then when a process would die, you'd have a free space up here, and you would then fill up a process in that free space. Then when another process died, if there wasn't a new process to fill it up, you'd have an empty space there. Okay, so it's not like your homework assignment when you're running jobs on CPUs, and when one CPU comes free, you have to fill that free CPU. Okay, so here, when this process finishes, that leaves this spot empty. Okay, and then when a new process comes along, you can put that new process in that spot. But as processes come and go, memory ends up being fragmented. You have a free piece here, a free piece here, a free piece here, and a free piece here. At some point, you want to compactify or compress memory, for example, it might be worth your while every once in a while to take A, B, and C and shove them all to the top. So there's a 1, 2, 3, 4 chunk free at the bottom. So you would have all these processes moved up and then have one big chunk at the bottom. So we could have this, this, and this used and have all this stuff down. We could have all this free if we wanted to. Okay, we could push processes A, B, and C to here, here, and here, and have this one, this one, this one, and this one free. Okay. Base and bounds virtual memory causes fragmented memory, but it's relatively straightforward to unfragmentate memory. But you have to copy a chunk of memory from here to here and then update a memory management unit. But copying memory from here to here is bad enough that that's the big problem with this system. Fragmentation is, unfortunately, it's solvable, but it's too slow. Copying programs from here to here or from here to up here, copying programs to defrag memory is just not acceptable. So from an engineering point of view, when this was invented in the 60s, it was better than what they had before, which was the relocating loader, which had fragmentation and had when you defragged memory and you copied one process from there to up there, you had to translate as you copied. Okay, base and bounds fixes that a little bit. You don't have to do translation as you copy. You just copy from here to here and then update the base register. So that's a big improvement, but you still have to do the copying. Okay, so fragmentation is still considered a problem here. Okay, now there's actually two. We're going to see that. Let me write a little note. There's actually two kinds of fragmentation. Okay, there is what's called internal and there's something called external. Okay, they're a little bit hard to explain in words, but okay, let's try to explain this idea. What we've been talking about so far is external fragmentation. This fragmented memory is outside every one of these processes. Okay, so the memory that's lost to us, or that for example, if memory looked like this, we'd have a hard time loading a program that needed 3 chunks. Okay, in a sense, if we can't relocate these, we cannot run a program that needs 3 chunks of memory. So the memory would be lost to us because it's in chunks. We can shove all the allocated memory up to the top and get one big free chunk. Okay, so we can defragment. Yeah, so that case we would be defragmenting memory. Oops. Yeah, we can defragment, but while it's fragmented, until we defragment, we refer to this broken up free memory as external fragmentation, because the fragmentation is on the outside of the processes. Now, think about this system here. In this system here, this program has the same size virtual address space as this one and this one. So all the programs have the same size virtual address space. But not every program has the same amount of code and uses the same amount of data. There might be some programs that really don't need anywhere near that much virtual address space. So it could very well be that process C is barely using any of its virtual address space. It's only using maybe it's only using half of its allocated virtual address space. That's called internal fragmentation. Okay, internal fragmentation is when you've allocated memory to a process, but it doesn't really need what you allocated it. You've over allocated memory to a process, maybe because if you have this idea that every process has the exact same virtual address space, so the bound register for every process has the same value, you could be creating what we call internal fragmentation because you're wasting memory. You've got memory wasted in here because process C doesn't need all its space. And you may have some memory wasted in here because process A doesn't need all its space. You fix internal fragmentation in this case by making everybody's virtual address space a different size. So that's what the bound register is for. The bound register is actually for solving internal fragmentation. So internal fragmentation is solved using the bound register. You only give a process a bound register that's big enough for what it really needs. So if a process doesn't really need a lot of virtual address space, it can be given a smaller bound register. And another process that needs a larger virtual address space, it can be given a bigger bound register. Okay, so this system can deal with internal fragmentation, but it's hard for it to deal with external fragmentation. The only way to do external fragmentation is solved by copying and updating the base register. Okay, you solve external fragmentation by actually I should say you solve it by defragmentating. Okay, you solve external face by defragmentating, and what you do to defragment is you copy each process and update its base register. Okay, so if you have a lot of external fragmentation, like in this picture, there's a fair amount of external fragmentation. You solve it by defragmenting, but that means like you would copy process, well, in this case, you would copy process A up to here. The smart thing would be to copy process A up to here. The dumb thing would be to move process C up to here, move process B up to here, then move process A up to here. But a clever algorithm would realize that to defragmentate this, it needs to copy process A. So it copy process A up to here, then update A's base register from 3,200 kilobytes to 64 kilobytes. Okay, right. So a real important idea in the whole notion of virtual memory is this idea of fragmentation, internal fragmentation and external fragmentation. The base and bound system can deal with internal fragmentation reasonably well, as long as you know ahead of time how much space a program needs. You can give the program that much virtual memory space by setting its bound register. You set the program's bound register and you give it just the amount of virtual memory space it needs. Okay, right now, but that causes, okay, now there's still another problem here though. What if a program wants to grow at runtime? Like, here's a good example. Suppose process C is my text editor. Okay, how much memory does my text editor need? Think about it. How much memory does this process here is TextPad? Okay, can you tell me when I launch TextPad how much memory it needs? Why is it undetermined? Somebody wrote that it's undetermined. What's undetermined about it? Right, exactly. Because like right here, suppose I decide to open a really large file. Okay, so for example, I could just open some really large file. And so right now, for example, TextPad's just got a little bit of text in it. So it's in memory. No, when you edit a file, all the data from your editing is in the program's memory. The program is, it's data the program's manipulating. When you open a file, when I go to open a file, TextPad doesn't know until it actually opens the file how much memory it needs. So programs, realistically, on a modern computer, programs need to be able to grow. Now, you could just allocate every process a massive amount of memory. Okay, but that's not, but then if you allocate everybody a massive amount of memory, to assume the worst case, what does that do? What does that cause? Suppose you try to play it safe. So you allocate every program some massive amount of memory. Like you give every process half a gigabyte of you give every process a half gigabyte of virtual memory. Why would that be a bad strategy? Exactly. You're almost guaranteeing lots of internal fragmentation because lots of processes won't need all that space. And then you'll still have the case that some processes need more than that. We actually need a system for processes to grow, as they're running. Okay. Now, in this case, what that would mean is, and I don't even know if any operating system ever did this. You would want a system where when a program's running, the process could ask the operating system to increase its bound register. Okay. You know, you would grow a process, like take B here. B could potentially grow, like suppose the memory looked like this. Right now, B's bound register is 64 kilobytes, but there's some empty space down here. What if B at middle of its runtime said, hey, operating system, I want to grow. Please increase my bound register for me. Now that would be a privileged operation. So that would mean that the process would have to do a system call to the operating system, and it would be a change bound system call. There'd be a system call to the operating system saying, would you please increase my bound by a certain amount? Okay. Now, in this case, the operating system could say, well, there's a bunch of empty space below process B. Sure, I'll increase its bound. Okay. Now, what about process C? Suppose process C wanted to increase his bound. Would that be doable? Okay. Can you think? Suppose C wanted to grow, so it did this system call to the operating system saying, please grow my bound register. Could that be done? Okay, it'll hit B, yeah, right, it'll hit B's memory space. So what would you have to do? Could you grow process C? Yes, move it. You could do it if you would say, okay, but we're gonna have to it's gonna have to do some work. You could move process C down to here and give it a larger chunk. So that means you would have to move it, update its base register, and update its bound register, and then you could grow process C. Okay, so base and bound can actually, so now base and bound over here, base and bound can actually take care of growing the virtual. Okay, you can grow the virtual memory space. You can grow the virtual memory space by changing the bound and maybe moving the process. Okay. Okay. So these are the issues that we want to deal with. Now, when we get to the more modern system, the page table, the whole point of page tables is to solve external fragmentation, internal fragmentation, and growing a virtual memory space in a super efficient way. The real task of a modern virtual memory system is to take care of the internal, external defragmentation and growing a process problem in a really efficient way. Now, base and bound can solve these. Base and bound can actually solve them, but in a fairly clunky way. The clunky thing is copying. Okay, notice that to defragment, we had to copy. To grow a process, we may have to copy. Okay, we may have to copy the process in order to grow its virtual memory space. We have to copy the process to defragmentate the external fragmentation. Okay, So, but we can see by thinking about this, we can see how these problems can be solved. Okay, base and bounds deals with internal fragmentation relatively well. It deals with external fragmentation not too well. Okay, it deals with internal fragmentation reasonably well, external fragmentation not really all that well, and it doesn't deal with growing processes all that well, but it can do them. Okay, all right, all right, okay. Now, whoops. Let me think. Try to remember what the. No, so we've used the example in this chapter here while we were talking. If you go to this chapter, this is the chapter on base and bound. He kind of has the same pictures. Okay, here's his picture of a virtual address space. Okay, so this is the picture of a virtual address space. Notice he's written in some addresses in there. Okay, those are virtual addresses that we want to like here, so these are machine instructions. See, think of this as code sitting in that section of virtual memory. Okay, and the addresses are, see, based on 0. Okay, then this is going to get loaded into physical memory. So here's the physical memory picture. This picture here is just a blown up version of, I'm sorry, this picture here. So this picture here and this picture here are the same picture. Notice he's using a 16 kilobyte size here, and he used a 16 kilobyte size here. This virtual memory space sits inside of this physical memory space. So this picture here is the same as this picture here. Okay, but over here, he's still assuming, see, 16 kilobytes, 16 kilobytes, 16 kilobytes. Okay, now what he's done here is he's imagining this process is sitting inside here. So it's sitting inside this one. The code's up here, the heap is there. Okay, so he's using the same idea. So he's gonna, it's same picture copied from this chapter to this chapter. Okay? And he's gonna explain, and in this place he explains how to use the base and bounds. Now, if you look in this book, you'll never see this picture. Okay, you don't see this picture in the book, and I think that's actually, I wish he did this picture here, because this is the picture that really makes you understand how the memory management unit sits between the CPU and the physical memory, and it does the translation using this formula here. This formula is in the book. The formula right here, but that's the formula without the test. See, he tells you the key idea. The physical address is the base address plus the virtual address, but there's really a test in there. You have to test whether the virtual address is trying to go past the bound. So the test he mostly just says in words. So he doesn't write it in this more, this way, using C code says exactly what the address translation is. Check if the virtual address is less than the bound. If it's okay, do the translation. Otherwise, raise the exception. Okay, so there's the translation part of the formula. Okay, the actual raising exception he describes in words here. Okay, notice he does some examples of virtual address to physical address translations. Okay, notice, but there's nowhere in here. There's nowhere in here where he draws this picture. Okay, and this picture, I think, this is one of these cases where I think the picture really explains way better than the words would. Okay, the picture, from the right point of view, with this picture, you can really get a sense of how base and bounds is working. Okay, so you should be able to draw this picture from memory. Your goal right now from this point of view would be to remember, we started with this version of the picture. This version of the picture explains the idea, but leaves the memory management unit empty. Okay, so this is the idea of address translation. virtual addresses over here have to be somehow translated into physical addresses over here. But the implementation inside here, okay, that's empty. Okay, now we've learned one real implementation you can put inside that box. You can put two registers in the memory management unit, the base and bound register, and then you put a little bit of hardware in the memory management unit that does this formula, and now you have a working memory management system. Okay. In the next chapter, what we're going to do is we're going to put multiple pairs of base and bounds registers in here. Okay. Let me see. Let me save this picture. Okay. The idea of the next chapter is to if base and bounds work real well, what we're going to do is we're going to use multiple pairs of them. So let's imagine we have two pairs of base and bounds registers. So let's see. So I'm going to draw four registers in here. See if I can get four registers and fit in here. One. Ah, okay, so there's now four registers in here. Okay, and there's going to be base one, base two, bound two. Okay, so this will be base one. This will be bound one, then base two, and bound two. Okay. Now what that means is a program now has two chunks of, what we're going to do is we're going to imagine a program as being made up of two chunks of physical memory. So a process, imagine this will be just one process now. One process could have allocated to it two chunks of physical memory. Okay. Maybe it's allocated two chunks of physical memory. Okay. Now what that means is that this might be the value, like over here is base two. Base two is this address here. That's the base of one chunk of physical memory. And then base one maybe is over here. Okay, so base one, suppose base one points to there, and base two points to there. Base one's bound would be the size of this chunk of physical memory, and bound two would be the size of this chunk of physical memory. Now a program's got two chunks of physical memory allocated to it. Okay. Okay. This could be, we'll see that this idea can become very useful. That now this is really not done anymore. These are called segments. When you do multiple pairs of base and bounds, they're called segments. So this would be segment two, and this is segment one. So you would refer to this as, this program now has two segments. So this is segment one, and this is segment two. Okay. Okay. why would you do this? This actually is how Windows worked and Linux worked. Both Linux and Windows both did. Linux and Windows never used base and bounds. Base and bounds is really kind of old. But this idea of segments was actually in the early days of Windows and Linux was used. Every process could have, we'll see, actually every process could have multiple segments. The processes could have, I I think on a Pentium, they could have 4 or 5 pairs of base and bound registers. They could have 4 or 5 segments. I forgot how many there were in a Pentium, and they're still there. And Pentiums still do this. Okay? But processes could have multiple segments. Okay. The idea was there was a couple reasons for doing this. One idea was if you go, whoops, um, I lost the. If you notice, this program is really in this process is really in 3 pieces: the program part, the heap part, and the stack part. At one point, it was thought, well, then why not have that sit in virtual memory as 3 segments? A code segment with its own base and bounds register, a heap segment with its own base and bound register, and a stack segment with its own base and bound register. That was actually thought at one time to be a very elegant way to design a process, that a process would be 3 segments. One of the reasons was this idea of growing. If a program needed to get to grow its heap, and the heap was its own segment, you could grow the heap without having to grow the whole process. Similarly, if a program wanted to grow its stack, it could grow its stack segment without having to grow its heap segment. Okay, so it turned out to be that by breaking a program up into multiple, like the code segment would rarely ever grow. When a process wants to grow its virtual memory, it was almost never because you wanted to have more code in the program. Programs don't generate code on the fly. What was much more likely is that either the heap wanted to grow or the stack wanted to grow. And more often than not, it's the heap that wants to grow. When programs need to grow, it's usually because they need to allocate more objects. Okay, so this idea of base and bounds and this idea of the ability to grow the virtual memory space by changing a bound register, that was the people said, well, why don't we just have multiple base and bounds registers? Okay, that would it was thought to have less. Oh, now if you look at this picture here, all this gray area in here, that's internal fragmentation. Okay, that would be what we were referring to. That's an example of this internal fragmentation. Okay, it's there so that the heap can possibly grow or the stack can grow. But notice that only one of them can really grow into there. If the stack can grow a little bit and the heap can grow a little bit, but if they grow a little bit, then there's a lot of empty space here. If the stack grows a lot, then the heap can't grow very much. If the heap grows a lot, then the stack can't grow very much. On the other hand, if they bump into each other and you want to grow the whole process, if you think about it, if the picture looks like this, growing the whole process when the stack and the heap have bumped into each other is nearly impossible. You could change the bound register, but if you change the bound register, notice that that's giving you more space at the wrong end. You need space in the middle. This is what people realized, that this is what they were really, when they tried to grow a virtual process, by growing the base register, if your memory was laid out like this, it didn't work very well. If you grew the base register down this way and your stack was growing this way, you would have to move the whole stack down. So not only would you have to first move the process in memory, then after you move the process in memory, the process would have to move its stack, which is very, very, very inefficient. So to it, even though a single pair of base and bound registers solves this internal, external, and growing virtual memory, it does it in a really messy way. Lots and lots and lots and lots of need of copying. Okay, so to get rid of a little bit of the copying, they started adding multiple pairs of base and bounds registers. Okay, so for example, if you have two base and bounds register, you could have one base and bound register be the program and the heap together. Okay, notice that if you change the, if it's supposed, so you would have the base register would be here and the bound might be right there. And that would give you room for the heap to grow. And then if the heap needed to grow some more, you could move the bound register down here and the heap could keep on growing. Okay. Now, then your stack could be in a different base and bound register. Now you'd make your stack grow downward, just like the heap grows downward. You put the base of the stack at the base of the base 2. You'd put the base of the stack here at base 2, and then let the stack grow downward. Then when the stack needed to grow, you could change the stack's bound. So with two segments, you could have a fixed size code segment and a growing heap segment, and a growing stack segment with very little internal fragmentation and much less copying going on. Okay, so a single base and bound register solves these problems, and then multiple base and bounds registers solve these problems even a little bit better. Okay, and that's called segmentation. And that's actually most of the next chapter. The next chapter, the reading for that's this chapter here on segmentation for next week. The chapter is medium long. It's not very long, and it's mostly just saying, you know, here's that same picture again. You've got the heap growing this way and the stack growing this way, and there's all this wasted space inside here. And he wants to point out that this, with a single base and bound register, this doesn't work very well. If the heap and the stack hit each other and you need to grow this, it's really hard to grow it. You really want to break the heap and the stack into their own segments. Okay. So he basically describes that idea in this chapter. Okay. So it's not a whole lot of new idea. What we're really going to talk about next week mostly is this. This is the big idea. This is the modern virtual memory system, paging. If you look at the table of contents of the book, chapter 13 introduces the idea of virtual address space. Okay, we skipped 14 for now because that's about Linux. We're gonna replace 14 with Windows code, so we'll kind of go back to 14, but we'll translate everything into Windows code. That's going to be your fourth and last programming assignment. Okay. Base and bounds are chapters 15 and 16. Chapter 15 is a single pair of base and bounds register. Chapter 16 is multiple base and bounds registers. Okay. Then paging is going to be 1, 2, 3, 4, 5 chapters. Paging is complicated enough that it takes 5 chapters to describe paging. Okay, so we'll say a little bit more next week about segmentation, about pairs of base and bound register. So we'll go back and we'll talk about pairs of base and bound register and talk about segmentation. Okay, but then we'll also next Monday start talking about paging, which is that's what real modern operating systems do. They do paging. But paging is complicated enough that it takes 5 chapters just to describe it. Okay, and we're going to see that the goal is to basically do these things better and better. Deal with internal fragmentation better, deal with external fragmentation better, which means dealing with defragmentation better, and also the ability to grow virtual memory space. We want processes to be able to grow and shrink, because when a process, like in TextPad, if you think about TextPad, if TextPad loads a huge text file, it needs to grow its virtual memory space. But then if somebody closes that huge file, why should TextPad continue to hang on to a huge amount of virtual memory when it's not using it anymore because the user closed the big text file? So processes should be able to shrink too. So grow, and we want to be able to, and shrink virtual memory space. Okay, we want to be able to actually both grow and shrink. The shrinking will help us eliminate internal fragmentation, because if we know we're not using some of our memory space, we can just shrink our virtual memory space. We'll also see that we want to one of the things we'll talk about later on is we want process to be able to share. We'll see later that it's going to be very useful for the idea that processes can. This is kind of a weird idea. On the one hand, we said that our whole goal was that process C cannot touch process B's memory, and process B cannot touch process C's memory. But it turns out that what if process B and C need to work together? For example, a good example of that is Chrome. If we call up Task Manager, remember, Chrome is actually a whole bunch of processes. Okay, so Chrome itself is in memory, like this might be one piece of Chrome, this is another piece of Chrome, and this is another piece of Chrome. And they actually need to work together because they're really one process. So it turns out that even though our goal is to make it so that these processes can't touch each other, then we want to backtrack and say, but let's give them a mechanism so that they really do want to touch each other, we can let them. If we really do want to let process B see inside of process C, we can let it. But the process B and C have to agree to it. But there will be a way for processes to share their memory. They have to, the operating system lets them do this. The operating system has to have both processes agree to it, but it's useful to actually be able to say process C should be able to see inside of process B sometimes, okay? We can actually do that with multiple base and bounds registers, so we'll do that on Monday. We'll see that not with a single base and bound register, but if we switch to multiple base and bounds register, we can actually let two processes share a segment. Okay, so we can let processes share a segment, but then the virtual memory system the virtual page memory system will let us share processes in a really elegant way. Okay, all right, so so next week we're going to do chapter 16 briefly. There's not a lot in there. Mostly we want to talk about the sharing. How do segments let processes share? And then we'll start talking about paging. Okay, and that'll be chapters 18, 19, 20, 21, 22, 23. It's a long, there's a lot to talk about in paging. Okay, and at this point, we're done. I mean, it's time to quit. I'll try to these drawings I made that I modify. I'll put them into the I'll save them and I'll make them part of the file that I uploaded to the website. So this I'll make them part of this zip file. Where is it? This zip file here. I'll put the drawings I made, when I modified it, I'll make them part of this zip file. Anybody have any last minute question? Okay, so if you have questions about the homework, please let me know. And okay, so I'm going to stop the sharing. Let's see. Oh, I can just I'm going to end. So I'm going to end the meeting now. Bye.